All right, so I want to run through PA1, talk about some observations and some lessons from PA1. I want to talk about PA2 and get you started on that. I pushed the deadline for PA2 back a week, so it's due a week from today, which means you probably won't get 24-hour turnaround on grading for PA2, okay, because Monday I teach all day till like 4, so you probably won't get PA2 graded back next Tuesday, but I'll get to it sometime through the week. PA1 is graded and posted with feedback. I want to run through the ODPs that I wasn't here for, and I want to run through today's ODP. I want to talk about the quizzes if we have time. If not, we'll go through them tomorrow, and I'll probably push back the deadline for the first quiz because I want you to have a week to work on that at least. And then we'll go back to talking about data structures. So let me talk about PA1 first. Okay, just sort of some takeaways from PA1. So first punchline is people did a really good job with PA1. Okay, it's a confusing, complicated assignment in a lot of ways because this idea of data structures is probably new to most of us, and it's a different way of thinking about variables and a weird way to use arrays, right? In this case. Plus we're using a structure. So in most cases, at least some of the algorithms I saw looked pretty perfect, okay? And that's good. There's details that can make the whole thing blow up, right? And that's bad because then your code doesn't work, but it's good because details are small things, and we'll talk about some of those details in a bit and how to nail those down. But by and large, PA1 looked really good. Okay, so I tried to give you feedback based on what I saw and stuff. So PA2, I'm going to start grading from the back of the alphabet because it takes me, I don't know, like 15 hours to get through all of these, and sometimes by the time I get to the end of the alphabet, my brain is working differently. So you might not have as much feedback. So next time I'll start grading from the back. But I tried to give you feedback on where I think we were with the code, and if things weren't working, what you can look at. But the general feedback is come and talk to me, right? If you want to go over anything in your submission, anything that didn't work, anything that worked but you weren't sure why it worked, or you thought it worked and it turns out you lost points for it, right? Ask in class, come by office hours, shoot me a note, something, right? We can iterate on it. So specifics on PA1. Okay, first specific, make sure you have a make file. Okay, from this point forward, pretty much every assignment you ever turn in for a class is going to involve multiple pieces, usually in different files. And if you turn in a directory with several .c files and a .h file, and there's no make file, you're leaving it up to the intelligence of whoever is grading your assignment to figure out how to compile your pieces into an executable. And sometimes it's just gcc-o main star.c. But sometimes you have, 3 or 4 versions of your search function in your directory, search 1, search 2, search 3, and search that you were using for debugging and stuff. You only want to compile search, not search 1, search 2. And if you just say star.c, it'll say multiple instances of search and it won't compile. Right? So the make file takes all that mystery out. It lets you decide how do these pieces get turned into an executable, and the person who gets your code to grade it will just say make, enter, and it'll do what you told the make file to tell the system to do. Okay, so make files are really important. And I try, this is why it takes me like 15, 20 hours to grade, I try as much as possible to work with your code. If I try to compile your code and it says, undefined function main, and it won't build an executable, right? I'll usually go into your directory and I'll look at your make file and I'll try to figure out, oh, you forgot to include main.c. Or you didn't call it main, you called it pa1.c, right? Or, something else, and I'll compile it up. If I compile it and it actually doesn't compile, sometimes I'll look at your code and it's like you have a comment at the beginning with your name, but you put a single slash in followed by your name instead of 2 slashes. And if you just say /my name, that's a syntax error, your code won't compile. So what happened? Well, the person forgot their name, so at the last minute, they went ahead, they added the comment with their name, but they made a typo and only put in 1 slash. And they submitted it and they didn't try recompiling it. Well, I'm a reasonably good programmer. I can figure that out. I can put another slash in there and I can compile your code, okay? So part of what we're doing here at Clark is learning to program. Part of what we're doing here at Clark is getting ready to transfer to a university. Okay, for most of you, that's going to be in September. And things are different at different schools. If you go to a school where your classes have 100 people or 500 people in them, your assignment's probably never going to be seen by the instructor. It's going to be seen by an underpaid TA who's given a stack of 100 assignments to grade and has their own work that they have to get to, right? So if they compile your program, they say make, and it says can't make, they're going to give it a 0 and move on, right? They're not paid to look at your code to figure out how to compile it. There's no interest in doing that. And if they can give you a 0 and move on, that's quicker for them, right? And this is just the reality of taking programming classes at a large institution. So you really want to make sure you get in the habit now of any time that you make a change to your code and resubmit it, make really sure that code works, right? Even if it's a minor change, even if I just added my name to the beginning of it, just say make. Make sure that it rebuilds, you know? If you push something over to Git, you know, at least once close to the end, try pulling it back down, try cloning it into an empty directory and say make and run it and do your test cases. And you know what? Maybe somewhere along the way, you started pushing into a different repository, linked list test, with the intention of eventually taking your code and pushing it into linked list 1. And maybe you forgot about that because that was a week and a half ago. And so you think you're done, and your final code is in this new repository, linked list test, and linked list 1 has a README from 2 weeks ago and nothing else. Well, I have your Git ID. I can go on to GitLab and I can search in your thing and see all the repositories that I have access to, and I can say, oh, this one was updated 2 hours ago, and I'll send you an email and say, hey, is this where you put your code? It's like, oh yeah, sorry about that. Okay, I want to be able to grade your code, right? You're working on it. I'm spending time and energy teaching you. You're spending time and energy applying and learning. I want to be able to, at the end of all of that, look at your code and see what you got done and see that it works, or help you figure out what didn't work. Okay, so I'm vested in your success. But the underpaid TA, right, or the stretched too thin teacher, or the jaded professor or whatever, right, assignment's not there, it's a 0. So we're trying to sort of like get ready for you know, that kind of environment. And once you're done with school and you get on the job, right, and you've got a project that's due at 8 a.m. on Friday, and 8 a.m. on Friday the team gets together and they don't have your piece, well, what does that go to your boss as? This person didn't finish their piece. Well, you might be out of a job by the end of that day. So you know, habits basically, and figuring out ways to try to minimize the chance of these things happening. So this is all good stuff we can practice here. Meanwhile, on the side of data structures, and this is in some ways the easier part of it all, right? Because when you're programming, you sort of control your universe. So here's what a linked list typically looks like. So this is the Sentinel. And for PA1, the Sentinel was always stored at index 0 in our array. It's going to go away in PA2. We don't have an array. Our first data node is stored here, and so I use the term data node to mean a node that actually contains part of the data in our list. This is technically a node, but it's not part of the list. It's just there to point to the first node. So this is actually the first data node. And if the first thing in your list is 5, right, this is where your 5 is. All right, so here's the thing. This is the Chatty Cathy doll. Always start at the sentinel and follow the link of change from one node to the next, right? So start at the sentinel, follow the pointer to the next node, follow that pointer to the next node, follow that pointer to the next node. That's the only legitimate way to go through a linked list like this. Okay, it's always the same. And keep doing that until the pointer to the next node is actually not a pointer at all, it's our flag, which was my null in PA1, null in PA2, and then you know you're at the end of the list. So how do you search for a number in your list? Start at the sentinel, follow the chain from one node to the next, and at each node you get to, see if that's got the number you're looking for. That's the legitimate way to search for a number in your list. The non-legitimate way to do it is to go through your array from 1 through 99, check to see if array bracket I dot number equals the number I'm looking for, and array bracket I dot valid equals 1. That will tell you if the number's in the list or not, but it's not following the idea of a data structure called a linked list. Okay? And that latter approach, the non-legitimate approach, will not work for PA2. Why? Because our array would be all of memory. We have to go through every location in our memory looking for our number. And when we find our number, how do we know if it's part of the list or not? There is no valid flag, right? So PA2, the only way to look for a number, start at the sentinel, follow the links from one node to the next. How do you print? Start at the sentinel, follow the links from one node to the next. When you add, make sure that you insert the number right before the first number that's bigger than it. That keeps your list in order. You can always insert at the beginning, and then when you're ready to print, you can do a sort on the array, right? Pull out all the numbers that have a valid equal to 1, sort them, and print them out. That will print the numbers in your list, but that's not using the linked list as a linked list. Okay? So if you follow this convention, right, then PA2 is a small sideways step from PA1. If you did things like actually search through the array to find your number and stuff like that, you're going to have to rewrite your add function, your delete function, whatever function you did that in before you can move over to PA2, because it just doesn't port. All right, so in PA1, our sentinel was always at index 0. That was just a magic location, okay? This first node, is it always at index 1? No. It could be. The first time you insert something, it definitely will be. But suppose I insert the number 2, so that now this is the number 2. That's going to be stored at a different index, right? That's going to be stored at index 5 if it was the 5th number I inserted. And this last node, if my list is full, is that going to be index 99? Not necessarily. If I insert 99 things and the last thing I insert is the largest, then yeah, this will be index 99. But otherwise, it could be anything. So how do you know if your list is full? Do you check index 99, see if it's valid and points to null? No. Right? That's totally not following what the linked list says. How do you know if your list is full? See if you can get a node. Call your getNode function. If it returns null, your list is full. Or start here and follow a list of nodes and see if you've gone down 99 nodes. Along the same lines, you never really need to do anything with a valid flag except in getNode and releaseNode. Because if you're following the nodes in your list from one node to the next, every node in here must have valid equal to 1. Because the only reason the node shows up in this chain of nodes is because you added it. And when you added it, you did that by first calling getNode, and getNode sets the valid flag to 1. Now, it doesn't do any harm to check the valid flag, but in PA2, there is no valid flag, right? So you're going to have to figure out how to get rid of that check. But you know that everything in here is going to have a valid flag of 1. And you also know that anything that has a valid flag of 1 in the array is going to be in this list somewhere. So kick that around, see if it makes sense. All right, scanf. Let's say you want to scan I followed by an integer. only way to know if it succeeds is to see if the return value is equal to 1. The only way to know if it failed is to see if the return value is not equal to 1. If this is not an I followed by an integer, this return could be 0, could be -1. If you have an extra field over here, the return value could be 2. Okay? Always, 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 if you want to know if it found what you were looking for, how many things are you trying to match? See if it returned that number. If I'm looking for 2 integers, make sure that a scanf returns 2. If you want to know if it failed, don't say if it's equal to 1 or if it's equal to 0. Say is it not equal to 2. Okay, that's least likely to get you into trouble. The other thing you can do is if you're trying to do something like just find the command P, try not to do something like this. Right? You can do that, but it starts getting into weird return values because you're not asking it to convert anything. And so this will return a 1 or a 0 or a -1, but it kind of breaks the definition. And there's no need for this, right? If I want to know if my string starts with a P, which is really what this is asking, just say if string bracket 0 equals character P. And if you want to know if it's a P followed by a new line, you could also see if string bracket 1 equals quote \n. Or you could use string compare and see if your string compared with double quote P \n returns 0. And so on. So scanf, right, play around with it, write some test code, make sure you understand how to use that. It's a really powerful tool. Makes your life a whole lot easier in general, except when there's something about it that you didn't realize. And then it makes your life miserable. That's how a lot of things are. All right, let's talk about commenting. So again, most schools that you transfer to are going to have pretty strict commenting guidelines. They're going to want lots of comments. So I've asked you, when you write a function, to put a comment block in the beginning of the function that describes what the function does, the inputs to it, the output from it, anything the user needs to know about calling, any unexpected side effects, right? So what does your add function do? Well, it takes a pointer to a sentinel node. That's good to know. It takes a number, and it adds the number to the list so that the list is in increasing order. Well, that's good to know, too, because, you know, your add function could just add to the beginning, or it could add to the end, or it could add at a random spot. Well, it adds in increasing order. That's a big chunk of your code, right? So that's worth knowing. What does it return? It returns a flag, an integer. 1 means this, 0 means that. Well, that's good to know, too. What else? Can you call it with a number that's already in the list? I don't know. It's a good thing to know. So you know it because you wrote the code. But if somebody else is using this, do I have to check to see if this number is in the list, or will it somehow let me know if I try to insert something that's in there? Well, if it's not in that block of comments in the start of the function, what do they have to do? They have to read your code and reverse engineer it and say, okay, so previous and current, and if I'm going through and I check to see if this is bigger, right? Nobody's going to do that, right? Nobody's buying your code is going to do that. Nobody on your development team is going to do that. They're going to say, we can't use this code. None of the functions are documented. And if you go back to this, right, you know, later on, you're getting ready for an interview and you want to brush up on linked list code and you want to look at your code, you're going to have to figure that stuff out. You're going to be reverse engineering your own code 2 years after you wrote it. That's not a lot of fun, right? So you got a nice block of comments there that says this is what happens, and you just look at the code and figure that out. So what am I getting in a lot of submissions? Integer, add, parentheses, struct node, star, list, comma, integer number, close parentheses, comment, add. Well, yeah, that is what the function does. Or maybe add to list. Yeah, that's also what the function does. More is better, okay? I've never had this is not a challenge. I've never had somebody turn into code with too much commenting. Okay? You can put War and Peace in a comment block, don't. But it's really hard to go wrong with more good commenting, okay? So if I equals 0, comment, see if I equals 0. Not a very useful comment. Okay, if I equals 0, comment, is this the sentinel node? Well, that's a good comment. Now I know why you're checking to see if I is 0. And I know this block of code is firing if we're looking at the sentinel node. That's really useful when you're debugging or trying to integrate. Right? So good commenting, that's what I mean. Comments that tell the person something they don't know just from reading the line of C code. Right? I equals I plus 1, increment I, not very useful. I equals I plus 1, add one more element to the array, yeah, that's good. So definitely put your name in the code. I still got code without names on it. Put your name on the code. Comment block in the beginning describing the program, what it does, the course, the assignment number, the date, that kind of stuff. Name, CSE 222, PA1, linked lists. Well, that's a good start. What about linked lists? Right. This code implements linked lists using an array of struct nodes. It lets the user do various operations on the linked list and see the results. That's plenty. Right? You can go further. The user can insert, delete, search, blah, blah, blah. That's even better. Right? But somebody looking at this executive summary, right? Someone without a lot of patience, give them a synopsis of what this program is. And again, it's for your use too. Right? Where's that program I wrote that does such and such? Well, you'd like to have something that tells you what the program does. Okay, on the same note, indenting. Indent your code. Okay, for a few reasons. One, again, a lot of schools, they run your code through automatic grading systems. And some of these systems, if your code is not indented, it kicks it out as a 0. Right? Automatic, no ifs, ands, or buts. Now you got to find a teacher, find a TA, and argue your case. And that's a lot of work. But more importantly, indenting your code will help you write cleaner code. Okay? The most common problem I see again and again is something like this. Right? Something like that. And the intent is to execute some while loop, and then at the end of the while loop, return. And people will spend hours trying to figure out what's wrong with their code. It's not doing what it's supposed to do, something buried inside all of this. And the whole problem is that the return statement has been written inside the while loop. Why? Because they added an if statement here and they forgot to put in a closing curly brace. And when the compiler told them they were missing a closing curly brace, they just added it down here because that's where it said it was missing from. Right? Because that's all the compiler knows. And now this return statement is actually sitting inside the while loop. So the first time through, it returns. And it's not doing the while loop at all. Okay, and this is really hard to detect, right? Unless you're indenting. Now, if you're indenting consistently, right, your while is sitting here, the whole body of the while loop should be indented like this. And if you're indenting, your return statement is going to be indented over here, and then here's going to be a closing curly bracket, and you're going to look at that and say, right away, oh, I'm returning inside my while loop. That's not what I wanted to do. But you only know that if you're indenting. So it really helps you when you're writing your code to keep track of what's going on. And levels of indentation is just one of these things that can really trip you up. So a consistent indenting style is really, really critical. I'm not imposing a style on you. Other places will. Schools will. Places you work will. They'll say you have to indent 3 characters on each line. And if you have an if statement, the curly bracket has to come after a space on the same line as the if. and the else has to begin indented an extra 2 spaces, and it has to have else followed by no space followed by an opening curly bracket. Right? You'll get a whole style guide that tells you how to write all of these things. I'm not doing that to you, okay? This is the Wild West. But have some kind of coding style that's consistent for you, okay? It will really, really help. And it's good practice. And once you're in that mode, right, switching to a different style is just a matter of getting used to their habits. Or, you know, you write a little script that converts your indenting to their indenting, which is easy if you're consistent. Okay, so last comment on the subject of coding linked lists. Here is probably the #1 issue that I see people running into. And I don't know how long it took me to get past this, but it was definitely not a fast process. Let's say we want to print the contents of this list. So we're going to have some kind of, probably a while loop. And we're going to start at the sentinel. That's the only handle we have to the list. And the first thing we want to print is the data value of the node the sentinel points to. In other words, this block right here. And we want to print that, follow to this node, print that, follow to this node, print that, and then stop. Okay, the trickiest part of dealing with this or a lot of other data structures is setting things up so that exactly that happens. So that you start and the first node you print is this and the last node you print is that. As opposed to accidentally printing the sentinel node first, or accidentally skipping this first node and printing the second node first, or stopping before you've printed the last node, or trying to print a node after the last node and segfaulting, or finding that when your list is empty, what worked in this case no longer works because of the way that you got to this first node somehow doesn't work when this thing says my null. Okay, these are edge cases. They're sometimes called fence post problems. I call them edge cases, and they are always tricky. Okay. And the code that I'll show you, the code that you'll see, the pseudocode we'll go through, works in general, but it depends on how you're writing your code. Now, if I show you a piece of code that works and you copy it word for word, character for character, and type it in, it'll work. But that's not what you want to do, right? You want to use this as a guide to help you write your code. Well, if you write your code slightly differently, the exact code I write may not work. So for example, I can start off with previous equals sentinel and next equals sentinel arrow next, and I can start by printing next's data. Or I could set current equal to sentinel next and next equal to this node's next, and I can start by printing current's data. Well, if I do that, I have to check ahead of time to make sure current's not null. If I do the former, I need to make sure that next is not null. So sometimes I need to check in the beginning of my loop, sometimes at the end. Sometimes I want to exit when my node is null, sometimes I want to exit when my node arrow next is null, right? And I don't want you to try to figure out the rules for, do I check this at the top or the bottom? Do I check to see if this is null or if this thing dot next is null? There are no rules for this. What you really want to do is take however it is that you're writing your code to move through the list from node to node, and think about these edge cases. How do I start? How do I end? How do I deal with an empty list? If I'm adding, how do I deal when there's no room left to add? Right? The edge cases, the extreme points. Think about that with respect to your code. And it's trial and error, right? Not just blindly putting something in, but it's thinking about it and saying, okay, I think I need to move to the next node in the beginning of my while loop. Well, go through it and see if that makes sense. Does it start correctly? Does it get the last node and then stop? And you may find it works great, but it skips the last node. So what do? Well, you just do an extra print at the end to print out the last node outside the loop. Well, that may work perfectly unless your list is empty and then it segfaults. So while you're figuring this out, you're trying different things, you're working with this on paper, right, not in code. That's helping you develop the intuition to deal with these edge cases in the future. And it's just a practice thing. got to keep at it, and you got to work through it. You got to do the switch, right? But the more you do this, the more that intuition will develop, and eventually you'll see something like this or some other weird data structure you've never seen before, and you'll say, oh, okay, well, I'm going to write it like this. And it'll just come naturally. Okay? So don't be discouraged with it. This is, you know, if your code blows up every time you say print, yeah, that's a problem. But again, you know, I'm trying to sort of like look beyond that. But in the bigger scheme, right, that's not a big issue. Right, if it's just a problem with stopping too soon or starting too late or something like that, work with it, pin it down, okay? And it will click at some point. And it'll be like, oh no, I can't do that, I have to do this. No, it'll be, like I say, I don't know how long it took for that to happen to me. I'm sure it was more than a few weeks. But it does get easier. And the amount of time you have to stare at it and struggle gets to be less and less. You get a better version for you of drawing these pictures, a better way to think about it. You get really fast at writing down, you know, something that looks like this, and it starts to snowball. And that helps you not just with this, but every time we talk about a data structure, we're going to have pictures to go with it. And so by the end of the course, you'll have some pretty good circuitry for dealing with this stuff. And we'll be doing data structures in spring, you'll be doing data structures at university, so it's an ongoing thing. So even if your code segfaults sometimes, right, it may be like really close to perfect. And it's digging into these, it's playing with GDB and drawing pictures and so on. All right, does that make some sense? All right, let me run through the ODPs and then we'll start talking about PA2. So 206, I think we already did. Let's do 207 and 208. So 207, you were basically building a little tiny linked list. You had two nodes and you wanted to link the first node to the second node. We didn't worry about data values or anything like that. You basically had two nodes. You want to change the first one to point to the second. And we're not creating nodes here, we're being given two nodes. So this is link A comma B. And the picture is, here's node A, here's node B. What you want to do is link them together like that. That's the only thing your function should do. And if you think about what a struct node is, if this is n, this is really n arrow data, and this is n arrow next. So n, right, assuming that we declared this somewhere, struct node star n. N is a pointer to a struct node. That means it's an address. Okay, PA1 was an index. But it's something that points to a struct node. The node itself, the thing that it points to, looks like this. In memory, there's a piece of data, which we can get to by saying n arrow data. And somewhere near that, there's a piece of data, which we can get to by saying n arrow next, which is a location of another node. Just like n, it's a struct node star. So since that's another n, we could say n arrow next arrow data and get to the next node's data if we wanted. We'll do that later. But on this, our goal is to set up A's next field to point to B. And it's pretty straightforward. N1 arrow next equals N2, or A arrow next equals B. Okay, it's one line of code, it's 11 characters with a semicolon. It doesn't seem that complex, right? This is incredibly complex. There's so much going on in this one statement. And there's so much that can go wrong in this one statement. For example, do I want to say n1 next equals n2 or n1 equals n2? Or star n1 arrow next equals n2, or n1 arrow next equals star n2, or maybe n1 arrow next equals ampersand n2 because I wanted to point to the address of n2, right? There's so many different things that can go through your head with this, and this is pretty much the only one that works. So yeah, it's only one line of code, but figuring out how to come up with this, right, that's the learning part of that ODP. And when this makes sense, you're a big step towards getting on top of pointers and data structures. So n1 arrow next equals n2. Well, so let me rename these n1 and n2. Right? If this is node n, this block down here is n arrow next. If this is n1, this is n1 arrow next. So the value of n1 arrow next is stored right here. Now I don't write numbers in there, I write arrows, but when I write this arrow, what I really mean is the thing stored in here is the address of this thing it's pointing to. Well, it's pointing to a rectangle. What's up with that? I don't have a rectangle to store the address of, right? We usually point it to, you know, the middle of this top half of the rectangle, but what we really mean is we want to point to the location where this rectangle begins, where the structure begins in memory. That may not be where the data is. The data might be somewhere after that. But we're really saying we want this to be the address of this block. And that's what N2 is. It's the address of this structure. So when we say N1 arrow next equals N2, it's really taking this address, putting that in here. Convincing yourself that that's the right thing, that takes some meditation and some picture drawing and some trial and error and some GDBing eventually. But once that clicks, once that starts to make more sense, right, it starts to get easier after that. So that's what this ODP was about. So the weekends ODP takes that further, and it builds a linked list out of thin air. It creates 4 nodes, it chains them together, and for extra bonus, it just sets the data values of those last 3 nodes equal to x, y, z, the arguments to the build function. So this is like the previous ODP, except you need to construct the nodes yourself. That means calling malloc. You need to set the data fields for these last 3 nodes. Well, that's just, you know, node arrow data equals x. That's not too bad. And then you need to link all 4 of them together. Well, that's doing ODP 207 3 times. Link that first node, which we're calling the sentinel, to the second node, second to the third, third to the fourth. And then return the address of that first node. So it's really ODP 207 plus plus, right? And then mallocs thrown in there. So this is decidedly more than 1 line of code. But it's really 3 things being done. The first thing is a bunch of mallocs. So send N1, N2, N3, those are just the pointers to my 4 nodes. When we say malloc, malloc will return an address that's big enough to hold one of these nodes, and I set each of these pointers to that address. So this creates those 4 rectangles with nothing in particular in the boxes. And then this sets the top part of those last 3 nodes, the data fields equal to x, y, z. And then this is ODP 207 done 3 times. Chain those things together. And then also the last node set the next field equal to null. This is in some ways easier than 207. Because 207, you got to figure out how to do this the first time. Once you figure that out, 208, yeah, okay, so you have to learn mallocs, that's new. But the linking part is already something you've done at least once. All right, so 209, this is today's ODP. You're given a pointer to a chain of 3 nodes, and there's no sentinel node in here. I just want you to think of this as 3 nodes that are chained together, like this picture. Okay, so PTR is what you're given to the edit function. That's the address of a node. That points to a second node. That points to a third node. And the goal of your function is to update something in this list so that the middle node basically disappears, so that you delete this node in the middle. And how do you do that? Well, basically we want to change pointer so that instead of pointing over here, it points over here. That's all you got to do. Now how do we do that? Well, we know how to set a value here. It's just PTR arrow next, but what value should we give it? Well, we need to give it the address of this node. And how do we find that address? Well, it's only stored one place.
Storage in the middle nodes.next.
Yes, it's stored right here in the middle nodes.next. Well, how do we get to the middle node? We need its address, and that address is only stored one place. That's in PTR's next. So if we start with PTR next, that will give us the address of this. We can call that middle. If we look at middle arrow next, that's this field. That's the address of this node. We can call that last. And then we can say PTR arrow next equals last, or just middle arrow next. And bang, your middle node is gone.
Do we need to free this like an arrow?
Yeah, I wasn't sure. I would say go ahead and free it, just to be safe. But I don't think I checked for that. All right, so let's take a quick run through PA2. So PA2, same structure as before, except the next field, instead of being an integer, it's a pointer to a struct node, which is still kind of an int, but it's a location in memory. When we get to the end of the list, this will have the value null instead of mynull. So you don't define mynull anymore, you just use null. That's defined for you in standard io.h. So that's built in. Your init function should return an empty list. That means a sentinel that points to null. In your main program, instead of declaring your list as struct node list bracket 100, which limited you to 100 nodes, you're going to define it as struct node star list. That's also an array of struct nodes. But we're not going to set up that array ourselves. We're going to get that from init. And init is basically going to use malloc to create a sentinel node and return that sentinel node to us. And that's very ODP-ish. And then all of these functions are exactly the same. So add, print, delete, search. You've done those in PA1. They behave exactly the same. You pass them a pointer to a struct node, which is what you passed in PA1. So that's what an array of struct nodes is. And you give it a number if there's a second argument, and you update the list accordingly. So they act exactly the same way. We'll go through pseudocode for these and look at some implementation tomorrow. The main program, exactly the same. I think I clarified some things on PA1, and I haven't done that here, but all your functions do exactly the same thing. Right, so insert, print, search, delete, and X. The one addition is when you exit your program, you got to free all the memory that you malloc. And we'll talk about that tomorrow also. There's a function you have to write to do that, but it's pretty straightforward. It's basically just going through the list, but as you walk through the list, you free up the memory behind you. And when you get to the end, you're done. So we'll talk about that. Everything else gives you a synopsis of legal commands. Same deliverables as before, GitLab repo named linked list 2. Okay, and a bunch of people already have that up, so that's good. And all the rest is the same. So we'll talk about the quizzes tomorrow. I'll adjust dates if necessary, but I want to get you going on a GDB quiz because that'll help you with ODP, with PA2. We'll talk about the last ODP tomorrow, and then we'll start digging into the details of coding up PA2. And by the time we're done with ODPs, you've already done versions of most of what you have to do in this next assignment. But we'll see how some of this code looks. We'll look at it in terms of algorithms. And you should be able to finish that in a week. All right, so we'll start from there tomorrow.